What's up, team? Today we're talking exponential decay. Learning targets down below. I can create and evaluate an exponential decay function. So here we go. We know all exponential functions are in this form. F of x equals a times b to the x. We know a is our initial value, b is our multiplier, and x tells us how many times to use our multiplier. If you don't remember that or that doesn't make sense, please watch the previous video. It's all there. So I'm assuming you understand that piece and we're moving forward. Exponential decay. The difference between exponential growth and exponential decay is, well, simply one goes up, one goes down. That's a big deal. But in terms of what the function looks like, it's really all this b value. This b value tells us if it's going to be growth or decay. If the b value is greater than 1, it's a growth problem because it's getting bigger. If the b value is between 0 and 1, like in this compound inequality here, then it's going to be an exponential decay problem. Today we're focusing on exponential decay. We're going to do one example, and that's it. So, you know when you buy a car, if you go to a car dealership, brand new car, drive it off the lot, it loses value pretty quickly. The car's not worth what you just paid for it. It's kind of a weird phenomenon in our world. But the longer you have the car, you get the value for it or whatever. But if you try to sell it, like even a couple months later, you're not going to get the price you paid for it because it's used. It's worth less money now, and it continues to lose value as it ages because of wear and tear, issues with it, new maintenance, whatever the case may be. So here's our scenario. Say we went and bought a car. We paid $20,000 for this brand new car. We spent a ton of money on this thing, and it's brand new. It has all the shiny things that you could wish for. Well, let's say that a car depreciates in value, goes down in value about 20% every year. I don't know if that's actually the case. That's a number I made up for easy math. So let's say it goes down 20% every year. We are going to create a function to model this situation, and then we're going to evaluate. We're going to figure out. We're going to make a prediction of sorts, how much the car is worth after 5 years using that information. So here I captured all the things. New car is 20 grand. It loses 20% of its value each year. We're going to model it, and then we're going to figure out how much it's worth after 5 years. So we need to identify our A, our B, and then that's enough to have us create our function. And then for this last piece here to evaluate, we need to plug in that number for X. So our A value, pretty straightforward. The initial value is 20 grand, right? So our A is $20,000, or just 20,000 for the purpose of this function. The B, it's really tempting to say 20, but it's not 20. If we said our B value is 20, that means we're multiplying the initial value by 20 every year. That means it's like if you had $1, then the next year that's worth $20 and so on. That's crazy. The value's not going up. So we know our value is going to be somewhere between 0 and 1, but we need to figure this out. So we have a 20, and it's between 0 and 1. What the heck? So if we're losing 20%, well, that means we're keeping 80%, right? Because if 100% is a whole, then if we're losing 20% of it, we still have 80% left. And if you remember decimals and percentages and whatnot, if we have 80%, that's the same thing as 0.8. So recall that 100% is the same thing as 1, and 80% is the same thing as 0.8. So if our car is worth 80% of what it was when we bought it after year 1, well, then that's going to be our multiplier. So B is 0.8. Great. Let's create a function to model this thing. So we're just going to follow this pattern. F of x equals a times b to the x. We have a a, we have a b. We're going to leave it in terms of x for the time being. So f of x equals a times b to the x. Lastly, how much is this car worth after 5 years? That means we're going to utilize our function notation. We're going to evaluate f of 5. This should not say a times b to the x. I should have put numbers in here. Let's fix that. So instead of a, we're going to put in 20,000. Instead of b, it's going to be 0.8, and x is going to remain x. There we go. So that's actually our function. We could graph that. We could see what's happening. In fact, we're going to do that next after we evaluate. So 20,000 times 0.8, but now we're evaluating for 5, so we're going to replace the x with a 5. And I don't know what the answer is here, so I'm going to bust out my calculator. I hope you do as well. So remember in PEMDAS, I'm going to do my exponents first. So 0.8, and then I'm going to press that caret button to the 5th power, and I'm going to get this number, 0.32 blah, blah, blah. So 220 6,000 times, now I'm going to replace this with 0.32768, because that's what my calculator says. And then I'm just going to multiply this stuff by 20,000. I'm going to finish what I'm doing here. 20,000. My calculator tells me, it says 6553.6. So F of 5 is $6,553.60. So what does this mean? What's the point? Well, if this data is true, if it was all accurate, again, I made this up. I'm not sure that that's actually 20%, but I know that it's definitely something. It definitely goes down. After 5 years, after we spent $20,000 on a car, 5 years later, if this is all true, that car is now only worth $6,553. We lost over half of our value, but we had 5 years to enjoy our car. So it kind of depends on where you place your value. Okay, next we're going to look at a graph of this here function. Okay, now I'm over in Diesmoose. You'll see diesmoose.com/calculator. I've adjusted my y-axis here to go from -1,000 all the way to 21,000. And then my x-axis is here from 0 to 25. I'm going to type in my function, f of x equals 20,000 times 0.8 to the x power. And it puts in the graph for me. This is great. So let's try to interpret what is happening. We know when we bought the car, so it was 0 years old. See my mouse down here. It was worth $20,000. That's what this graph is telling us. After a year, you see a sharp decline, and it ended up being worth $16,000. When x is 1, the car was then worth $16,000. After 2 years, we track this up, it's worth, a hair under $13,000 or so. After 3 years, we're down here pushing $10,000, and so on. It goes down, 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 and you'll see when we typed in our 5, we got about $6,500. Yeah, that makes sense. It's right here between $6,000 and $7,000. You'll see it continues to go down, but it begins to level off. It starts to flatten out, and it never actually reaches 0. Because when you just take 20% away from something, it's never going to actually reach 0. So we could zoom in on this. Maybe this is too far out, but we could zoom in on it and see somewhere in here. It's getting smaller, but it's never quite hitting that 0. And we could keep going further and further and further. It's going down. It's getting closer to 0, but it's never quite touching that 0. So this is what a graph of an exponential decay problem looks like. Okay, with that is what I have for you for today. Check out the problems in our classroom. Let me know if you have questions. You got this.